Hello, you're welcome to another session, and this time we are going to look at confidence intervals. Uh, Here we look at the probability of a parameter falling between a set of values. For example, from the word interval, it means we have boundaries. We have two boundaries. So we look at the probability that a given parameter will fall within a given set of values. So confidence intervals measure the degree of uncertainty or certainty of any sampling method. So as we know that our populations are always big, so we always use samples when collecting data or carrying out research. And therefore, a sample should be able to estimate the true parameter of the population. And we always have that question in mind on whether the sample size is large enough to make an accurate estimate that is compared or inferred to a population. And therefore, we use what we call a point estimate to infer the sample mean to the population mean. So a point estimate is that specific numerical value of a parameter. And the best estimate we always use is the population mean. Mean is used other than other statistics like mode and median. We use the mean because the mean varies less than the mode and median. So as we are looking at confidence intervals, we're going to be using the mean. So therefore, when you're choosing an estimate, what are the properties, or what properties must it have? It should be unbiased, it should be consistent, and then it should be efficient. It should give the smallest variance of variation. So an interval estimate of a parameter is an interval range of values used to estimate the parameter. So for example, if I'm interested in getting the average range of year 2 students, the average age, so I get a mean or a specific age, then add and subtract what would be like the error, or what I estimate the error to be. So for example, if the mean age lies between 26.9 and 27.7, so if we can see that I added a 0.4 to 27.3 to get 27.7, and then subtracted a 0.4 from 27.3 to get 26.9. So what you add and subtract to the mean is what we call the error of estimate. So therefore, the confidence level of an interval estimate of a parameter is the probability that the interval estimate will contain the parameter, assuming that a large number of samples are selected. So three common confidence intervals are always used. We use the 90% confidence interval, 95% and 99%. And using what we call the t-tables or the limit theorem, that when the sample size is large, at 95% confidence level, the sample mean falls within 1.9 standard errors. So this is our Z value, the standard error, that when the confidence level is at 95, so that the mean will vary between this value, 1.96. So in our next slide, we are going to see how the 1.96 comes. So if a specific sample mean X bar is selected, there is a 95% probability that it will fall within the range of the population mean plus or minus what we call the error estimate. So likewise, for 95% a probability that the interval specified by this will contain mu can be denoted as this. So we see that here we are adding and subtracting the error of estimate. So meaning When I subtract it from the mean, I get what we call the lower boundary. And then when I add it to the sample mean, I get what I call the upper boundary. So this is basically the same as this, that the population mean will fall when I subtract the error of estimate from the sample mean, on that side of when I add the error of estimate to the sample mean. So since other confidence intervals are used, the simple Z alpha over 2 is always used in the general formula. So instead of the 1.9, we always use Z alpha over 2. But this is only used when the sample size is 30 and above. We shall get to that. And now remember that our error is the difference between because we always aim to be 100% accurate. So if you're confident at 90%, the error will be 1 or 100 minus 90%. So therefore, when at 95% confidence level, our alpha, so I'm expressing this as a decimal, so 95% as a decimal is 0.95. So my alpha at 95% confidence level, the alpha will be 1 minus 0.95, or the error, which is 0.5. Then at 99% confidence level, the error is going to be 1 minus 0.99, which will give us 0.01. Then at 90% confidence level, the alpha will be 1 minus 0.9, which will give us 0.1. So this is the general formula for confidence interval. Instead of the 1.6, the Z value for 95% confidence level, we now use Z alpha over 2. However, this only works when the standard deviation is known, and also when the sample size is greater or equal to 30. Otherwise, if it is less than 30, we shall have to use a different test. So whenever you come across a scenario when n is greater than 30, this is the formula we use. This is the standard deviation, which is always given, the sample size is always given, and then the Z alpha over 2 is got from what we call the T tables at the bottom. So from the T tables, because like I mentioned that the common confidence intervals are 90, 95, and 99%. So when we go to our Z table, here, I'm going to upload all these tables. So at the bottom, you see Z alpha. So these are the different values of Z alpha over 2 at the given confidence levels at 50%, at 80%, at 90%, at 95%. We saw the 1.6 in the previous slide, then at 98% and at 99%. So you just come to your Z table, then you choose out the value for Z alpha over 2 that corresponds to the given confidence level. So going back, so at 90%, Z alpha over 2 is, if I open my table at 90%, here is 90% confidence interval. The value of Z alpha over 2 is 1.645. So 1.65, we rounded off. Then at 95%, Z alpha is 95% is here, Z alpha is 1.696. Then at 99%, Z alpha is 2.576. 2.58, still we rounded off. So therefore, the term Z alpha into standard deviation over root n, this is called the maximum error of estimate. That this is the maximum error you can commit for you to be confident in this given, at this given confidence level. So the whole of this is our maximum error of estimate, and this is the likely difference between the point estimate of a parameter and the actual value of a parameter. So we have an example here that a survey of 30 adults showed that the mean age of a person in this vehicle is 5.6 years, assuming that the standard deviation of the population is 0.8 years. Find the best point estimate of the population mean and the 99% confidence interval of the population mean. So the best point estimate of the population mean, remember we said, is the sample mean. So the best point estimate will be the sample mean of 5.6. Now getting the confidence interval of the population mean. Remember, this is our general formula. Since our n, what is our n? Our n is already 30. When n is greater or equal to 30, then we use this given formula. So we are, what confidence level are we working at? 99%. So we have the sample mean x bar, which is 5.6. So we just substitute. Then from the t table, we can get z alpha over 2. And at 99% confidence level, what is our z alpha over 2? 99%. Z alpha over 2 is 2.56. 2.576. 2.57, you can round off to 2 decimal places. Then the standard deviation was given as 0.8, and then we have our n as 30. So you do your body mass. Now body mass at work. Brackets first. Once you do a mistake in the computation, or when simplifying, the answer you get will be wrong. So when we divide this by root of 30, what we get, multiply it by 2.56, that will give us 0.38. And the good thing, the value of this is the value of this. So you subtract 0.38 and you also add 0.38 this side. So what you get here should be the same as this side because it is the same expression. Once they are different, then one of them is either wrong or right or both wrong. So therefore, one can be 99% confident that the mean age of the vehicles is between 5.22 and 5.98 or 6, based on a sample of 30 vehicles. So we can now determine a sample size. Someone might ask themselves how you tell that a sample size is sufficient enough to give us a true estimate of the population. From the formula of maximum error of estimate, which is this, z alpha over 2 into standard deviation over root n. We set an n here, so which represents sample size. So all we do is to make n the subject of the formula, and that will be our formula for sample size. So we can start by putting n the other side, or root n, so that e comes down, and then to get rid of that root sign, we square both sides. So the square will die with the root sign here, and then we shall be left with z alpha over 2 times standard deviation over e, and everything squared will give us the sample size. So now the first scenario, we were working at confidence interval for the mean when standard deviation is known and n was greater or equal to 30. But now we want to look at a scenario where the standard deviation might be unknown, that is the population standard deviation, and when n is less than 30. So always look at the sample size. When it is 30 and above, use the previous formula that has z alpha over 2. But when the sample size is less than 30, we use what we call a t distribution. So a t distribution, like the normal distribution, is also bell-shaped. It is symmetric about the mean, and that's the mean divides it into 2 equal parts. The mean, mode, and median are equal to 0 and located at the center of the distribution, like the normal distribution. The curve still never touches the x-axis, but here this is what is unique, the last two, the variance is greater than 1. And then the t-distribution is a family of curves based on the concept of degrees of freedom, which relate to sample size. So instead of sample size, here we basically look at degrees of freedom. However, as sample size increases, the t-distribution approaches a normal distribution. So when the sample size reaches 30, then the t-distribution becomes a normal, or it approximates to a normal distribution. So here we are going to use degrees of freedom. And please note that degrees of freedom, to get degrees of freedom, we subtract 1 from the sample size. For example, if our sample size is 29, degrees of freedom are those values that are at liberty to vary. So if I have 29 elements, only 28 will be free to vary. So therefore, the degrees of freedom are sample size, or n minus 1. So this is how a t-distribution looks like. So as the sample size increases, it approaches a normal distribution curve. So degrees of freedom are a number of values that are free to vary after sample static has been computed. And we have an example here that if we have a mean of 10 values, only 9 are free to vary, 9 out of the 10. And therefore, the formula for degrees of freedom will be 10 minus 1, or n minus 1. So the formula for a specific confidence interval for a mean, when standard deviation, the population standard deviation is unknown, and when n is less than 30, we use T alpha over 2 since we are using a T distribution. We don't use Z alpha over 2. Please take note of this. Whenever you see that n is less than 30, this is the formula to use. We use a T distribution. So we have an example. We shall start by finding the T alpha over 2 value of a 95% confidence interval when the sample size is 22. So we saw our sample size is less than 30. So we start by getting the degrees of freedom, which are n minus 1. So 22 minus 1, our degrees of freedom will be 21. So another thing to note here, now we use what we call we still use the T table. So we look for 21 in the left column of the T distribution. So we still use our T table. And then 95% in the row labeled confidence interval. So we are working at confidence at 95% confidence interval. Then we look for the degrees of freedom. So we are working at 95%, but then we have 21 degrees of freedom. So 21 is here, and then 95. So our T alpha over 2 will be 2.080, which is this. So once we have that, we just substitute. So please remember that at the bottom of that distribution, we have Z alpha over 2 values. So we come and substitute in our formula to get T alpha over 2. So an example, 10 randomly selected plants were studied and their length was measured. The mean height was 0.32 centimeters and the standard deviation was 0.08 centimeters. Find the 95% confidence interval of the mean height, assuming that the variable is approximately randomly selected. So since the population standard deviation is unknown, we use the sample standard deviation, which is denoted by S. And then the degrees of freedom, remember our n is 10, it is less than 30, so that qualifies the t-test. So our degrees of freedom will be 10 minus 1, which is a 9. So the t-distribution is used. So we look for 95% and 9 degrees of freedom. So we go to our t-table, 95% is here, and then 9 degrees of freedom, which is it 2.262? Let's confirm. Yes. So this is our T alpha over 2 value. So we come and substitute it in the equation. We have the sample mean as 0.32. We have our T alpha over 2 as 2.262. Then we have our sample standard deviation as 0.08 and our n as 10. So still you use your body mass or law of precedence and can simplify. So therefore you can be 95% confident that the mean height of the population will lie in this interval based on a sample of 10 plants. So that is it with confidence interval when n is greater or equal to 30 and when n is less than 30. When n is greater than 30, we use the Z alpha over 2 value, and when n is less than 30, we use the T distribution. Please take note of that. Now let's look at confidence intervals and sample size. For proportion, we all know proportion just represents a part of a whole. So proportion can be expressed as a fraction, a decimal, or a percentage. So they also represent probabilities that can be obtained from samples or populations. So we shall be using the following symbols: P meaning population proportion, P hat meaning sample proportion, and sample proportion is given by x over n, where x is the number of sample units that possess the characteristic of interest, and n is our sample size. So for example here, if I'm interested in looking at agriculture and food science students, but then my interest is to find out how many agriculture students are in the class. So X will be the number of agriculture students. So X represents those units that have a characteristic of interest. So therefore, if this is our sample proportion, then the opposite of that, Q, will be, and remember we said that a proportion is just a part of a whole, so it is a decimal fraction of percentage, meaning if the entire sample is 1 or 100, what doesn't possess, or our Q, will be 1 minus P, or the complement. So an example, in a study, 200 people were asked if they were satisfied with their jobs. 162 said they were satisfied. So in this case, our n is 200. X are those people that have the characteristics of interest. These are the people that were satisfied. So our x is 162, and therefore our p hat, or proportion probability, will be x over n, so will be 162 over 200, which is 0.81 or 81%. So therefore 81% of the people were satisfied with their jobs. Now the proportion of people who were not satisfied or never responded favorably will be either 100 minus 81 or 1 minus 0.81, which will be either 0.19 or 19%. So confidence intervals for proportions. To construct a confidence interval about a proportion, one must use the maximum error of estimate, which is, for this case, it is Z alpha over 2 times the square root of the proportion, the probability proportion, times the complement of the proportion over n. So confidence intervals about the proportion must meet the criteria of, when we multiply n times the probability should be greater or equal to 5, and then nq should also be greater or equal to 5. So the formula for confidence interval is now this. So it is, we go back to our Z alpha over 2, then we can get P hat and Q hat. So now this becomes our error of estimate, and we always round off to 3 decimal places. So we have an example that a sample of 500 food technician applications included 60 from Maine. Find the 90% confidence interval of the true proportion of men who applied for the position. So since we are looking at 90%, our confidence as our confidence interval. Our alpha will be the difference. So when you're 90% confident, it means there is an error of 10%, or the difference will be 100 minus 90, or 1 minus 0.9. But remember, we said that we can get our Z value from the T table at the bottom. So at 90% confidence level, our Z is 1.645. 1.645, or rounded off to 1.65. So we can get p hat, which is x over n, and also q hat, which will be 1 minus p hat. So still we do the body mass, and what we get will be the confidence interval. You can be confident at that confidence level that men who applied were between 9.6 and 14.4%. So still from the error of estimate or maximum error of estimate formula, you can get a sample size for proportions. So this is our error of estimate. So making n the subject will give us a formula for sample size for proportions. So confidence intervals for variancy and standard deviations. So to calculate this, we use what we call chi-square distribution. And the chi-square variable is similar to the t variable because it is also from a family of degrees of freedom. And a symbol, what we would call x squared, represents chi-square. So a chi-square variable cannot be negative, and distributions are positively skewed, because whether something is positive or negative, when you square it, we get a positive value. So this is how it looks. And here two different values are used in the formula for confidence interval. One value is found on the left side of the table and the other on the right. So for example, to find the table values corresponding to 95% confidence interval, one must first change 95% to a decimal and subtract it from 1. So what we get here will be our alpha. So if you're 95% confident, our alpha will be 5% or 0.05, or that will be our error. So when we divide that by 2, we get what we call alpha over 2, and that gives us our x squared right value, or what we call chi-square right. So we go to the chi-square table and look for 0.025 at 95% confidence level. So this is our 95% confidence level. So, but then we also use degrees of freedom. So let me first look for an example that has the sample size. Here it was. So to get now the left value, remember we get the right value and the x and the left value. So this 0.025 gives us the right value. So a figure that corresponds to 0.025 and a given degree of freedom will give us the value of x squared right. Now to get the value of x squared left, we subtract the value from the value of alpha over 2 from 1. So here we got 0.025 as our alpha over 2. As our alpha over 2, so therefore to get x squared left, we are going to subtract alpha over 2 from 1. So still when we go to our chi-square table, we look for this value, and then where it corresponds with the degrees of freedom of interest will be our value for x squared left. So finally we find the appropriate row corresponding to the degrees of freedom. So a similar procedure can be done for 90% and 99% confidence level. So we have an example. Find the values of x squared right and x squared left for a 90% confidence interval when n is 25. So remember, degrees of freedom are n minus 1. So to find x squared, right, we said we subtract at the confidence level from 1, so to get alpha. So therefore 1 minus 0.90 will give us 0.1, and then we divide that by 2 to get alpha over 2, which is 0.05. So to find to find x squared left, we subtract what we get as alpha over 2, which is 0.05, from 1. So that will give us 0.95. Hence, we use the 0.9%, 0.95 and 0.05 columns, and the row corresponding to 24 degrees of freedom, since our n was 25. So when you go to our chi-square table to get x squared, right, remember x squared, right, was the first one that it corresponds to when we subtract alpha when we subtract the confidence level from 1 and then divide what we get by 2 to get alpha over 2. So we look for 0.05 and then the degrees of freedom, which are 24. So from our chi-square table, 0.05 is here, and then 24 degrees of freedom, which will be, I think, 36.415. Yes, so that is our value for x squared, right, or chi-square, right. Then chi-square left, remember we said we subtract alpha over 2 from 1. So the difference is 0.95. So we look for 0.95 and then 24 degrees of freedom. So 0.95 is here, and then 24 degrees of freedom, which is 13.848. So those are the values. So we can now use that to get the confidence interval of standard deviation and variance, or variance and standard deviation. So the formula is given by n minus 1 into sample standard deviation or sample variance over x squared, right? The one we've seen in the previous slide. And then the same to the other side, it is x squared left. So for standard deviation, we get this. Remember, standard deviation is the square root of variance. So if this is variance, standard deviation will be the square root of these two expressions. So for example, find the 95% confidence interval for the variance and the standard deviation of nitrogen content of a fertilizer if a sample of 20 parts has a standard deviation of 1.6 milligrams. So here they have not given us the mean, so we can only use what is given, which is a standard deviation. So therefore, since we are looking at a 95% confidence in level, our alpha will be 0.5 and the alpha over 2 will be 0.5. We divide it by 2. So this is our x squared, right? So we go to our table and look for what corresponds to 0.025 and 19 degrees of freedom. So 0.025 is here and 19 degrees of freedom, which is 30.19191. Did I see correctly? 0.025 and 19. Yes, it is 32.852, which is here. Then to get x squared left, x squared left, we subtract alpha over 2 from 1. So therefore we shall have 0.01 minus 0.025, and the answer will be 0.975. So you look for 0.975 with that corresponding degrees of freedom to get x squared left. And please note that if the exact value is not there, you look for the closest value. So 0.975, we go to our chi-square table, 0.975, it's there, and then 19 degrees of freedom, which is, I think, 8.907. Yes, so we have the standard, we have the variance or standard deviation. If the standard deviation is given, you square it to get variance. But if they are given variance, you don't have to square. You just put the value the way it is. We have the sample size. So when you do your computation, we get a range for the confidence interval of the true variance. So for standard deviation, since it is the square root of variance, we just get square root of both sides, and we shall be confident that the standard deviation lies between that interval. Thank you so much. Please read and stay safe.